Hey, okay, well, let's try this one again. So, I decided to leave the intro video. All the audio was there. The audio wasn't cutting out, and it's pretty short. So you can kind of listen to that one, sort of like a podcast. This one, though, there's a lot of images and demonstrations that I've been giving, and also the audio was cutting out. So I wanted to re-record this one for you. All right. So you know this, what we're looking at this time is we're going to look at how to describe and explain the nature of sound signals. But like I said, we're going to focus, we're going to end up focusing on speech, but we're going to start with the basic building blocks of sound. Okay. Just went over that. So what is sound? It's just the propagation of a pressure wave in space and time through a medium. And it's important that that medium has compressible molecules. If the molecules aren't compressible or movable, sound can't propagate. Similarly, if the medium doesn't have, if there's no medium, if it's like space, then sound can't travel because there are no molecules. The essential elements of sound in that case are a sound source, which for you, for any of us speaking, for speech language pathologists and for audiologists, the sound source is the vocal folds. Well, I guess also for audiologists it could be a hearing assistive device. In that case, the sound source is the assistive device, not the vocal folds. But anyway, we'll go with vocal folds for now. So the sound source, we've got a sound source. We've got vocal folds, right? Cool. And then medium, we've got that right here. It's air. So I'm making a sound in my vocal folds. It's traveling through the air to my camera where it's being picked up and transferred on to you through your speakers. What's essentially going on is it's creating a pressure wave. We'll talk about that in a second, but that wave is just traveling through the air molecules. You can see in this graph that I've got right here that air isn't the only carrier of sound. I mean, you've probably heard recordings of whale songs. That's moving through water. Water is a really good conductor of sound, or at least the speed of sound is greater in water than it is in air. You can see the speed of sound in water is probably somewhere between this liquid petroleum here and the human body, because it's somewhat like either of those two liquids. You can see that liquids, no matter what it is, they convey sound in a range, and that speed is much faster than in air. And then you can also see the last two on there, iron and aluminum. They also convey sound, and they happen to be a lot faster than either liquids or gases like air. You might know this, maybe you don't. I don't know. I mean, I think there's a variety of ages in our in this class, but even from there might be, I guess, a variety of interests. So maybe some of you will know. But in old Western movies, like they would show someone listen to the tracks to see if a train was coming, and they couldn't hear it in the air. Well, the reason for that is this. The sound is going to travel a lot faster through iron or steel train tracks, and also it's going to be less impeded by other things that can impede sound in the air, like other sounds that are dampening those sounds out. Though we're not going to talk about interference and masking for quite a while. But we will eventually. But anyway, these are all different types of media that sound can travel through. Air, liquid, and solid. And you probably know, if you enjoy science fiction movies from the 80s, which I absolutely do, that in space, no one can hear you scream. It's the slogan for Alien, right? I know this picture is not from Alien. I think this is from either Aliens or maybe even one of the later ones. But whatever, it's okay. The reason, and I kind of alluded to this already, but the reason why no one can hear you scream in space is there's no medium. There's nothing for sound to travel through. So, I mean, what's happening is, and we're going to talk about this in the next slide, but so let's say that I have my, I'm playing this creepy alien sound. I could do that in space, I certainly could. And all these little, like say I'm in a spacesuit and I can do that, and all of these are going to vibrate like they would normally, like they do in air. Because they're under tension. The reason why they're vibrating is because they're under tension. Not anything special about the medium. But their vibrations are pushing on the air. So without air in space, or without water, if I'm underwater, or if I was inside of a giant cube of iron, I guess, or whatever, without anything to push against, these are just going to vibrate and make no sound at all. You could have your ear right next to it. I could put them right next to my microphone, like right up to it, but not touching it. And if we were in space without air, there would be no sound at all. So the medium is definitely an important part to propagating sound. Certainly, well, I shouldn't say it's an important part to propagating sound. I mean, you can have something vibrating that would create sound in a medium, but without a medium, it wouldn't be creating sound. So the medium is essential to the sound, but then also you have to have the source as well. With a source and a medium, you have sound. So the answer to that old stupid question of if a tree falls in the forest and nobody's around to hear it, does it make a sound? It does, because you have a medium, which is air, and you have a sound source, which is the tree hitting the ground. So it certainly makes a sound. The only two things that are essential to make a sound are the sound source and the medium, not someone around to perceive it. All right, let's keep going. All right, so we've kind of alluded to this already with the vocal folds and my vibrating guitar strings. But qualities that a sound source has is that they need to be able to vibrate. There's two. They need to be able to vibrate, and they need to have mass and elasticity. Why do they need to be able to vibrate? Well, just like the guitar strings, that is what's pushing around the medium. And it's that pushing on the medium that creates the wave that's going to be interpreted as a sound. It's the regular pushing on the medium. So in sound we've got, if you remember from anatomy and physiology, I don't have I have a rubber band around here, but if you remember from anatomy and physiology, the vocal folds will be pushed open by air in small puffs. And it's this regular movement, this regular motion of these puffs of air that really creates sound. If it was just one, it would create a sort of sound. It might create like a click or some sort of sound, but to create an actual sound that we can really listen to, you have to have this regular motion. Now, there's going to be some things as we go on in class that we don't really need to have completely regular motion. You can have dissonant sounds that create irregular motion, but they still have multiple openings. There's still vibrations that are happening that are creating the sound. Just one initial thing is not enough beyond just a click. And a sound that's not a click is going to have a sustained amount of vibration, regular or not. Okay, so mass is the amount of matter present in the object. You probably know that from physics. The reason why that's important, though, is that to push molecules, to push air molecules, to push water molecules, whatever you're pushing. Whoops. Banging my guitar and stuff. Whatever you're pushing around, whatever molecules you're pushing around, they're going to have to be pushed around by a massive object. And I don't mean massive as in terms of large, like huge. I mean massive as in terms of something that has mass. Because the only thing that can push around something that has mass, and a molecule has mass, is something else with mass. So think about this tuning fork here, right here. That has mass. The end of that fork has mass. It's made of metal. And that big, like, massive chunk of metal is going to be pushing against molecules and setting them into motion. And that's what you see here is these little red lines, the regular motion of the air molecules being pushed around by the tuning fork. I've got the formula here for density as well. I'm not going to make you compute anything like that, so it's just here kind of for your benefit. But you're not going to have to compute the density from the mass or anything like that. Just know that sound sources need to have mass, and they need to be able to vibrate. And lastly, they need to have elasticity. So you can see that this motion here of whatever this is some sort of element created from a lot of molecules. We'll say it's a metal atom or something. Well, it wouldn't be an atom. Each one of those would be an atom. So it doesn't matter. It's some sort of molecule. So it's going to change its shape when a force is applied. And you can see that if you watch right here, boom, the force is applied and then it comes back. It springs back. So we're pushing on it and then it springs back. That's really important. That's what sets up vibration. Think about Play-Doh. Play-Doh, you can push on it and it's deformed when you push on it, but it doesn't spring back. So if a force is applied and it doesn't spring back, there's no vibration to Play-Doh, right? It doesn't bounce well. If you throw Play-Doh at the ground, what does it do? It just kind of splats, right? Now, rubber, you can throw at the ground like a ball, and it's going to bounce all over the place. So like those bouncy balls that you get out of those like quarter machines, those are just made of rubber or something like rubber that's probably cheaper than rubber. Those have elasticity. They're going to be pushed in by the force of you throwing it at the ground, but instead of just staying there like Play-Doh, it's going to bounce back. And that rebound is what causes it to bounce all over the place. The rebound in this guitar is what creates the actual sound. So if you can see, so I'm going to pull this way up and then I'm going to let it go. That's probably not great for my strings to be pulling it that far. It's going to make it loose, but see how it gets pulled way beyond and then it goes back. And that's what creates this vibratory sound. I'm pulling it away and it's trying to get back to where it wants to be. And that is elasticity. Which is what I said right here. It wants to return to its typical length after you stretch it. Your vocal folds do the same thing, right? So you have them adducted and you have them tightened, then you're forcing air between them. So when the vocal folds open, they're being stretched. So they let the puff of air through, the pressure, the subglottal pressure reduces, and then they're able to close again. They close due to partly elasticity. They want to oppose that stretch that the air is imposing on them. So then they close again. But then you keep speaking, so you build up subglottal pressure again, and they have to open again. And there you've set up vibration. I want to talk about equilibrium really quickly. That's what's kind of going on with my guitar string here. So it goes way beyond the midpoint. So right here, it's at rest. It's at equilibrium. All the forces are equal. And then as I pull it away, I'm pulling this way now. I don't know if you can see that very well. So, all right, so it's at equilibrium right now. Equilibrium, resting state. So I'm going to pull away from the equilibrium by stretching it off to what's my right, what might be your left, although it could be flipping the view, so it might be your right too. Anyway, we're pulling it way out. And then as I let go and it vibrates, what it's doing is it's been pulled way out, so it comes back towards equilibrium. But it's got so much speed, it's got so much momentum by the time it gets there, it overshoots the equilibrium point and it goes too far the other way. So then it wants to go back to equilibrium this way, it overshoots again, and it keeps going back and forth until it dies out and ends up back at equilibrium. Which is why you have this dying out loudness of sound, right? It doesn't change in pitch, but it does change in loudness until it goes away. That'll make a lot more sense to you by the end of this slideshow when we're talking about how to compute frequency, which is pitch, and well, pitch is the perception of frequency. And also talking about amplitude, which is intensity is the perception of amplitude or loudness. So anyway, that's equilibrium. It's trying to get back to equilibrium. Okay, let me shrink myself again. And we'll go back over here. And I want to look at this spring. So it's doing a similar thing. If you actually put a weight on a spring, it has an equilibrium point. It might be, so there's a spring, you put a weight on it, maybe equilibrium is here, but it's going to go way further down if you just like hang the weight on and let it go, because gravity's pulling it much further than where it wants to rest. So then it's going to shoot back up because of the elasticity in the spring. It gets up here, then gravity can pull on the weight again, so it's going to fall back, and it's eventually going to end up dampening out and resting at its equilibrium point. But it's getting back to the equilibrium point that creates those vibrations. And that's why vibrations dampen out eventually. All right, we've seen that. We're back at this slide. Oh, I've highlighted wave, because we're going to talk about waves now. There we go. Now they're in a band. All right, so let's talk about waves. Let me move my face. All right, so we've got two different types of waves. We've got longitudinal waves and we've got transverse waves. Sound is going to be a longitudinal wave. The reason for that is it's pushing, so the waves, the sound that's coming out, the puffs of air that are coming out of my vocal folds, or the puffs of air that are coming off of this moving, my guitar string is pushing on air molecules. And so that's a lot like what's going on this slide here with this little red diaphragm thing. So think of it like a guitar string in very slow speed. It's pushing, it goes further over, and then it pushes against the air. And what that does is it starts pushing on air molecules. So you can see that it pushes, and then there's a dark band. And that dark band continues to flow over to the right, my right again. And then it ends up with areas where there are less molecules condensed. We're going to talk about this on the next slide, but those are called compression and rarefaction. Compression is where there are more molecules together. Rarefaction is where there are fewer. But anyway, a longitudinal wave is when these particles are moving in the same direction as the wave. So if you look at these particles, see these red particles on there, they are being pushed in the direction of the wave. Now they're not moving with it throughout the entire duration of the wave. An air molecule from my vocal folds is not going to travel all the way to my microphone, which is actually down here. But, I mean, one or two might travel all the way. But most of them are just going to push on other air molecules, and it's the wave that's moving. But the direction that the air molecules are moving is in the same direction as the wave. Contrast that with a transverse wave. And that's when the particle is going to be moving in the opposite direction. Not the opposite, but a perpendicular direction to the direction the wave is moving. So if you, the second wave right here, this is a transverse wave. So the wave is moving to the right, but the particles are moving up and down, right? So they're vibrating in this perpendicular motion to the way that the wave is actually moving. And that is actually how light travels. It has this kind of transverse wave. Photons are moving up and down, and that creates a propagation of light, the actual light wave, as it comes towards our eye. It's setting photons in motion, but they're just being excited and moving around, not moving in the same direction as our eye. The drum head, boom, see that it deflects when the stick hits it, but it deflects in a wave that disperses across the entire head of the drum. Now obviously the drum head isn't moving towards the sides, right? It's just moving up and down, but the wave is propagating in the perpendicular direction. So the drum head is a transverse wave. Inside the drum, though, that's not at all true. Inside the drum, the movement of the transverse wave on the drum head, up and down, is pushing on the air column, and that then turns into a longitudinal wave that pushes the air molecules in the same direction as the air wave. So a drum starts with a transverse wave and then becomes inside of it a longitudinal wave. Pretty cool. Now, water is also kind of a combination of the two, although it's a combination of the two in an actual combinatorial way versus how the drum is. The drum is kind of like a two-step process in being a combination of the two, but water is like an actual combination. So you can see, and you can feel this, right? You can feel that it's a transverse wave when you're in the ocean if you're swimming, because you can feel yourself rise and fall, and you really haven't moved a whole lot. Over time, the waves will carry you towards the shore, and unless you hit, some undertow underneath, and that'll pull you the other direction. The closer you are to the shore, the more likely it is that the waves are going to push you in the direction that the waves are going as well. But still, when you're out in the ocean, you're bobbing up and down, and it has, relatively little influence on your actual direction of movement. So what you can see here is, there it is. So here we've got this little circle, and this particle of water is traveling in the circle. But you can see the yellow dot is down and up, and that you can see is a transverse wave, so it's moving down and up. But then it's also moving right and left. And so it's got characteristics of a longitudinal wave. So it's being compressed and rarefied, it's traveling up and down, and so in this way a water wave is a true combination of a longitudinal and transverse wave. The biggest thing that I want you to take away from this slide is sound is a longitudinal wave. Okay, so this again is just pretty much more of the same, just showing that it's a longitudinal wave. A couple other things that I want to show you here is that you've got these areas of compression and rarefaction. So compression makes sense. The air molecules are actually compressed with one another. You can see these dark bands and follow them, across the entire duration of this wave. In between those is an area called rarefaction. You can think about that as in these areas between these compressed waves, it's more rare to find air molecules because most of them are in these compressed zones. So that would be rarefaction. Another thing that's important to note here is that the individual air particles don't travel with the wave. That particle is actually my laser pointer, so I'm going to move that off. You can see that they travel, when I say with, they don't travel the entire distance of this wave. They travel with the wave, they travel in the direction of the wave, but they don't travel the entire course of the wave. So watch any of these red particles on here, and you can see that they get caught up in that compression zone, and then they kind of zip back and get caught up in another compression zone. So some, obviously, in the real world travel a little differently. Some might go further, but this is kind of in general, they'll go a certain distance and then come back. And kind of a population amount. Like in general, they'll move that much and come back. And you'll see on the next slide, that's related to the amplitude, there we go, of the sound. Again, compression and rarefaction. Compression is an area of high pressure. That makes sense. There's more air molecules there. So if there's more of something, you've got higher air pressure. I should also note that this is relative to the average atmospheric pressure in whatever space we're talking about. Atmospheric pressure changes day to day, hour to hour, with different temperatures and different humidities. So it's always in flux. But we're talking about the average ambient atmospheric pressure. And the way that you measure sounds is just they're changing the pressure, the average pressure, either high or low, of that average ambient air pressure, regardless of what it actually is. So you can see that when you have these compressed areas, it's pushing more molecules together, and that's then creating a high pressure area. This works similar to the motions of the lungs. If you took, any of the ASU, SHS, anatomy and physiology classes, you know about the difference in pressures for the function of the lungs. So it shouldn't be totally unfamiliar with you. More of these molecules together is creating a zone of higher pressure than the average ambient pressure. However, once this compression front moves forward, you can kind of see that here. So this is pushing again, it's going to push and it's going to make this compression front. Then where those molecules have pushed together and they're moving, then that creates a zone of lower pressure behind it, a rarefied area. So there's lower pressure there. So what that's going to do is it's going to then start pulling air molecules back in to fill that space up. Why is that? Well, it's a property of diffusion. That means that all of the molecules in any space want to end up in an equilibrium state, to bring it back to what we were talking about earlier. So the air molecules want to be in equilibrium. You've got some guy that's coming along playing one string on his guitar, and that's pushing the air molecules out of equilibrium. Then you have an area, so it's pushing them out of equilibrium and creating a zone of higher pressure, and then the air molecules want to come back into the zone of lower pressure behind the compression front. But then you've got this thing that's vibrating, so it pushes against the air molecules and sends them on their way. It goes back, creates this low pressure area, some air molecules come in to get it, but this is a vibrating object. Remember, that's one of the ways that we can create sound. It's one of the hallmarks of a sound creating object, I should say. So then that is vibrating, so it comes back again and it hits those air molecules again once they've filled up that rarefied area. So then it sends them on again, you've got another low pressure zone, air molecules come in, boom, they get hit again. And so then that creates this propagating wave that travels through the air. That's everything I wanted to say on this slide. All right, let's move forward. Yeah, here we go. So this is the same thing we were looking at. Now I want you to pay attention to this right here. It's pretty much the same thing, but it's a different representation. You can see the wavefront moves in. You can see how condensed those molecules are. Let's watch it again. So very condensed molecules, then it hits where we're watching, boom, that air molecule travels way out, and then you've got this low pressure zone behind it. If you look at the blue bar, that's actually showing the pressure throughout the course of that wave. It's a little misaligned, actually. I would have pushed it a little bit further to the right. The area of highest pressure should be right at the point where all those air molecules are compressed. This actually looks like it's trailing by a little bit, which doesn't make any sense to me. So this is not the best graph. It's good. It illustrates the point, but it could be more correct. Anyway, okay, that's pretty much it on that. Now here, take a look at this graph down here. Now we're going to talk about amplitude, the actual amount that the air molecules are moving. They're going to move more when something is moving more. So if the vibrating object is moving more forcefully, it's going to push the air molecules away further. That makes sense, right? It's got more momentum, so it's going to shove the air molecules away to a greater extent. Amplitude is related to loudness. Loudness is the perception of intensity. So loudness is a perceptual characteristic. Intensity is actually the measurable characteristic of sound that relates to how intense or loud it is. We measure that as a signal in amplitude of the signal. So you'll see all these waves, and the distance, usually it's going to be the distance that they travel up and down. That's the amplitude. I say usually because we can represent these things in most ways, but the traditional way to represent amplitude is the up and down axis. So you're going to be looking at amplitude, and then frequency is going to go across. We'll talk about frequency in a second. So watch this particle right here. It's kind of oscillating back and forth. And the amount that it oscillates back and forth, well, that's its amplitude. That doesn't have anything to do with the frequency. Frequency is pitch, or the note that it might be playing. So you can have high or low frequency, a high or low pitch. Pitch is the... I'm losing my words, man. Pitch is the perceptual component of frequency. So it's what we actually experience. You can have illusions of both loudness and pitch, where what we experience, how loud something is that we experience, is actually not how intense it is. Or the pitch that we experience is actually not the frequency that we experience. We'll talk about that more later. For now, assume that they're the same thing, because usually they are. But again, they're not always the same. So I should have a slide on this. I'll give you a slide on this that just lists what the perceptual characteristics are and what the actual measurable characteristics are. But perceptual characteristics are going to be loudness and pitch. Measured characteristics are going to be intensity and frequency. And intensity is often called amplitude. That's just another name for it. So intensity and amplitude are the same thing, and then frequency is a different thing. Okay, so we can watch how far this particle moves, and that's related to the amplitude, but it has nothing to do with the frequency. So frequency, think about that as how often does one of these compression waves move through a given space. Frequency, right, just means like how often does something happen. And so how often one of these wave fronts moves through a given space is the frequency of the sound. Amplitude and frequency don't have anything to do with each other. You can have a sound that creates a large amplitude that pushes air molecules really far away, but it could be slow or it could be fast. So they could move a lot slowly, or they could move a lot quickly. And it doesn't matter. They're not at all related to one another. So let's watch this. So the rest of this graph, so we've talked about the up and down component of it, but then we're kind of also measuring it through time on this axis right here, moving downwards. So if you imagine you put a pen in this red dot, and then this graph below it is a piece of paper, and you're just going to like pull up on it at a constant rate. So what it's going to do, this particle's moving back and forth, and you're pulling up at a constant rate. Let's say you're pulling it up at like 1 centimeter a second. You're going to pull up, and you're going to create that perfect zigzag pattern. That's called a sine wave. We'll take a look at that in a second. But it's going to create this pattern. So you've got time moving consistently downwards on this graph. Usually, again, it moves, to the right, but I've rotated this graph. And that's just showing how often one of these compression waves moves through this area, or the frequency of that wave. Okay. This is another graph that's kind of showing the same thing. It's actually showing that there's two different ways that we can represent what's happening with sound. Or with a wave, I should say, because right now what you're looking at is a transverse wave, because you can see this particle is moving perpendicular to the direction that the wave is going. So it's a transverse wave, but the concept is the same. So you can see this little highlighted region where the little red dot is. This graph right here is looking at a particular snapshot of space, x equals 10.25, and that happens to be right where this little red dot is. So over time, what does the little red dot do? And that's what it's showing. It's showing that it's changing in amplitude over time in just this one space. So from there we can measure amplitude. We can also measure frequency by looking at the time between the peak and the peak of this graph. There it goes. So we can look at peak to peak, like that. Now the graph on the right, this one here, is doing something different. It's actually looking at a snapshot in time, 27 seconds. So right there you just saw 27 seconds occurred, and it's showing us different locations in space right here. So here we've got spatial locations. We're only looking at one snapshot in time. So this is like looking at a whole bunch of different little red dots if we represented them on here. We still get amplitude because we can see how high or low those little red dots are. We're just measuring different ones in different places at a particular time. So we can still get amplitude. We can still derive frequency from that as well. It's just two ways of looking at the same information. Usually with sound signals, we're going to look at this. We're going to look at amplitude and time graphs and just measuring a single location. The single location is usually a microphone, or the ear, or something like that. It's the way that we experience sound, so it makes more sense to look at sound on a graph that way. That said, occasionally you might see graphs the other way. So always look at your axes to kind of orient yourself to what you're looking at. Most of the time in this class we're going to look at amplitude by time graphs and not the other way around. Okay, so we know that waves vary across space and time. We've just talked about that for the last half hour. Frequency, again, you know, is how often one wave cycle occurs. When you measure frequency, there's one thing that might be confusing. So there's a bunch of different ways that you can measure frequency, and the way that you should measure it is from the beginning of the wave to the next cycle. A wave always begins at 0, and it always starts in the positive direction. Why is that? Well, that's because you're going from equilibrium, or average atmospheric pressure, to high pressure. You don't have rarefaction occur first. You always have compression occur first. And you always start from average atmospheric pressure. So we're at average atmospheric pressure. I pull my string over and I let it go. And the first thing it does is push on the air molecules. So we start with compression and then we go to rarefaction. On this graph, compression is here, rarefaction is here. And so the amplitude is kind of looking at how compressed these molecules are, how much they've deflected from their initial position, and how much they've moved back to the rarefaction position. So you can always see compression is the positive side of the graph, side of the origin, side of the 0 here, positive, and then negative down here. So this is rarefaction. Okay, so the wave starts here. And if you think about measuring the wave in the number of times it crosses the 0 point, then that's going to give you some trouble. Or rather, I should say, if you measure it in terms of like when this crosses the 0 point, that could give you some trouble. Because you're crossing the 0 point here, which is fine. But then you cross the 0 point here. But that is not the time it takes for one wave cycle to go. That's a half cycle. Because you've only got half of the shape here. It goes up, and then it goes down, and that's a full wave. So you have to make sure that you're looking at crossing the 0 point in the same direction. So crossing the 0 point and going up, that's where you start. It's going to cross the 0 point and go down, ignore that. And then it's going to cross the 0 point and go up again. That's a complete cycle time. So that's one way to measure frequency. Another way to measure frequency is peak to peak or trough to trough. Those are both not going to confuse you as much. I should really quickly point out that we're dealing with sine waves here. And sine waves are kind of like your prototypical basic sound wave. If you don't know what a sine wave is, I'm going to show you. All right, so this is Audacity, and this is one of the programs that I'll show you later in this module to use to analyze sound. What we're going to do right now, though, is I'm going to generate a... let me make sure that I started recording this. I did, and my mouse is going totally crazy. Okay, okay, hopefully that stops. What I'm going to do right now is I'm going to show you how to generate a tone, a sine wave, in Audacity. So I'm going to go to Generate, I'm going to go to Tone. Let's make a, that's way too high. Let's make a 500 hertz tone. We're going to change the amplitude to 0.8. Amplitude in most of our programs is between 0 and 1.0. 1.0 just means like the highest signal, the loudest signal that you can actually generate in one of these programs. So it's capped. It can only go between 0 and 1. That's when you're generating it. I mean, obviously when you're measuring it, sounds are very loud. So actual amplitude can be very loud. This is just a quick signal processing note that you can skip if you're not interested in. When you're recording something and it gets too loud, sometimes microphones aren't capable of picking that much information up. So what happens is it starts peaking, is what it's called. And what that means is there's a little membrane in your microphone. It functions a lot like the membrane in your eardrum. So it gets deflected with sound. It only deflects so much. And when it gets to a point where it can't deflect anymore, that's when you end up with what's called peaking. That means that the sound is too intense for this little membrane to deflect any more than it already is. And so you lose some of the actual information in the sound. It'll sound crackly and poppy and not clear. And that's because it's too loud for what the microphone is picking up. What you can do in that case is you can turn your gain way down so it makes the it makes your microphone less sensitive to what it's picking up. You can put covers on your microphone to like stop some of the sound from getting to the little diaphragm. You can use a better microphone, one that has more dynamic range. And then, of course, if the sound is too loud, it can actually damage the membrane in the microphone, just like a sound that's too loud can damage your eardrum or your tympanic membrane, depending on if you want to use the anatomical terms or not. So, anyway, that's signal processing. All right, so I'm going to put this at 0.8 amplitude. It's going to go for 1 second. That seems about right. And let's see what it sounds like. That's a sine wave. Now let me zoom in and I'm going to show you what a sine wave looks like. Well, look at that. It's exactly what we've been talking about. So that's what a sine wave looks like. It's like these waves that we've been looking at, and that's what a sine wave sounds like. Just like that. Sine waves are interesting because they are our prototypical sound. This is what a compression and rarefaction wave would sound like if it was in isolation and didn't change at all. Of course, we can change our pitch, so it's not going to be just a constant sound like this, and there's harmonic overtones in most sounds, in almost every sound. I mean, it's hard to create a sound that doesn't have harmonic overtones. This doesn't when it's generated, though when it comes out of my speakers and goes through the microphone, it is picking up harmonic overtones. So by the time it plays out of your speakers, you're not actually hearing a pure sine wave. You're hearing something that's mostly a pure sine wave with a few harmonic overtones. If I record that, which I am. I have my microphone on, so I should be recording what's coming out of my speakers. If I went in and analyzed that signal that came through my speakers, you'd actually not see this perfect sine wave. You would see a sine wave with some other little harmonics in there. Okay, anyway. Where was I? Sorry. Lost myself in this. Oh yeah, sine waves are a perfect prototypical sound. In fact, this is what makes up all other sounds. So every sound that comes out of our, every speech sound we make, every musical sound that you hear, even that, is made up of multiple sine waves. A flute is very close to an actual sine wave, but then something like a G chord is very far away from an actual sine wave, and then something like a completely dissonant knot chord is even further from a prototypical sine wave. And yet, it's made up of multiple sine waves. A whole bunch of sine waves put on top of each other. There's something called Fourier Transform, which we're going to learn about in a couple weeks. Fourier Transform essentially analyzes a sound signal, and it will pull out all of the different sine waves in that sound. That's how we can figure out the fundamental frequency of things. The fundamental frequency is the lowest frequency in the sound, so that's how we can figure out the fundamental frequency. We can also notice where the harmonic overtones are and how accentuated or dampened they are. That pattern of accentuating and dampening the harmonic overtones is what creates formants, which are the characteristics of speech sounds that actually, create the real difference between E and and oo and and all that stuff. Those are formants. You can create the same, those are all voiced at close to the same pitch, and they should have the same harmonic overtones because I'm still the same speaker, but the intensity of different formant bands is in different places, and that creates the difference that you're actually hearing in those sounds. Anyway, all this to say, all sounds, all complex tones are made up of sine waves. All right, really quickly, since we're here, I want to show you what a Fourier transform would look like. So I'm going to highlight some of this. This is trying to figure out what sine waves are present in the signal, and the sine wave that's present in the signal just happens to be, this is estimating it at 502 hertz. There's a lot of settings that you can use in these different programs that do the fast Fourier transform, and they're pretty accurate. They're not 100% accurate because it's applying a huge algorithm to the complex tone that you're looking at. This one's really close. It should be 500. It's 502. If we changed, our size that we were actually looking at, it would change the estimate. Now it thinks it's 526, which is why you don't use a 256 window. You're going to want to use something larger. Of course, the larger you go, the more data you need. So, anyway, now I've gone back to 1024, and it thinks it's 498. So it's close, but it's not exact. More on this later this week. That's a sine wave. That's a blow pop. I don't know if anybody knows that commercial, but it's a... Anyway, I'll put a link to it. Okay, so let's go back to our slideshow and end this really quickly. All right, so uh-oh. I froze for a second. There we go. All right. So now we've talked about how to measure frequency, peak to peak, trough to trough, or zero crossing to zero crossing if the wave is moving in the same direction. So zero crossing up to zero crossing up, or even zero crossing down to zero crossing down. When you look at a complex tone, when we get there, it's not going to be so easy to figure out what the peak is when you're going peak to peak, trough to trough, or even zero crossing to zero crossing. Instead, we're going to have to start looking at where the actual wave repeats. So you can see that here. If we start here, where does the wave repeat? Well, right here. Very easy. And the reason why that's going to get more difficult is you might have like multiple peaks at once and then one trough, and then it repeats again. We have multiple peaks and one trough. So complex tones can get a little weird to analyze, but you can. All right, so once we've looked at this, there's one other thing I want to talk about, which is wavelength. Wavelength is the actual distance that it takes for one wave to travel, one cycle of a wave to travel. The higher the frequency, the shorter the wavelength. We're going to talk about that more in the very next slide, but that's what wavelength is. Okay, the last thing I want to mention is, how do you actually compute frequency? Well, we look at the time that it takes to complete one cycle, and then you take the inverse of that. So frequency is just the inverse of the time it takes to complete one cycle. Let me show you what I mean. So I forgot that this was a GIF when I put these little lines all over everything, so this is going to be kind of hard to visualize, possibly. But you can kind of see it when they stop. They stop right on, the peak is right on one of these lines, so is the zero crossing moving up, so the beginning of the wave is right on these lines. One other thing I want to mention, it says 1 second is the time between each of these little bands. It should actually say 0.1 second, and that you'll see why in a second. So alright, so how much time does it take for one cycle to pass? Well, if we go peak to peak, we can go, let's see, this is going to start here. So we'll wait till it stops. 1, 2, 3, 4, 5, but this is 0, so we're not going to count that. So it's going to take this duration in here. So it's going to go 1, 2, 3, 4. And it takes 0.4 seconds to repeat. Right? So 0.4 seconds for that graph to repeat. Here is, I'm on 0, 1, 2, 3, 4, and then I'm back where I started, at the top of at the peak of the graph. So it takes 0.4 seconds. All right, so if you look over here, here's our formula. Frequency equals 1 over t. Now we know that t is 0.4 seconds. The cycle time is 0.4 seconds. So we put that into our formula. Frequency equals 1 over 0.4. And then you just do the math. Frequency equals 2.5 hertz. Hertz is just the measurement for cycles per second. That's it. It's named after this guy whose last name is Hertz. What? His last name is Hertz and it's called Hertz? Yeah, it is. Presumably no relation to Hertz Donuts, and I'm very sad that we're in a quarantine because I can't go get my Hertz Donut right now. I guess, man, that's a really local reference. If you don't live in Tempe, you might not know what Hertz Donuts is. It's just the most fabulous donut you've ever had. And, I mean, they're like crazy, they're huge, they've got all sorts of weird stuff on them. They will put them into a shake, where they take a donut and blend it into ice cream, and then give you a shake. It's not good for any diet. It's not good for humans in general. It's probably actually good that I can't go there. Anyway, I'm getting sidetracked. Hertz is cycles per second. Hertz, the person that this named after, is the person who first proved electromagnetic waves existed. And, you know, we're talking about sound waves, but we measure light waves in hertz, we measure radio waves in hertz, we measure all sorts of everything in hertz. It's all frequency, it's all done in hertz. So this skill that you're learning for sound would also apply to electromagnetic waves. It would apply to light waves. It would apply to subsonic waves. And it's all hertz. And that just is cycles per second. Okay. So once again, wavelength is the distance it takes to complete one cycle of a wave. And this, I believe, is my last slide. Yes, it is. And this is just showing the relationship between frequency and wavelength. It's an inverse relationship. That's really the important thing here. The formula here is lambda, and lambda is just the wavelength. It's the symbol for wavelength. Lambda equals c over f. C here is the speed of sound in air, and again, f is frequency, like we just saw on the previous slide. So wavelength equals the inverse of frequency, essentially, is what we're talking about. So what that means is a higher frequency, so let's say 250 hertz, has a much shorter wavelength than 25 hertz, has a much longer wavelength. So bigger number in frequency, smaller number in distance. Littler number in frequency, bigger number in distance. That's really it. What you're looking at in this picture that like totally sucks is a little piccolo, and piccolos, if you don't know, they're like tiny flutes. They're even higher than flutes. It has a very high frequency, a high pitch, which means it has a short wavelength. And this down here is, I think it's a clarinet, but let's just call it a bassoon, which is even lower. So a bassoon has a very low frequency, and you can see that it has a much longer wavelength. Okay, so this is just a review of what we looked at, and I'm going to leave that up while I finish up here. So this is what we looked at. The next few modules are going to be lectures from Dr. Deliri until you get to 1.6, and then I'm going to teach you how to use Prot, Wavesurfer, and Audacity to measure speech signals. And maybe, if I get bored, also some music signals, like one guitar chord.